The orbital flatness of planetary systems. Why flat orbits? This is by Harvard-Smithsonian Center for Astrophysics, phys.org. The planets of the solar system all orbit our sun more or less in a plane. Compared to the Earth's orbit, which defines the plane at 0 degrees, the orbit with the largest angle is Mercury's, whose inclination is 7 degrees. The angle of the orbit of the dwarf planet Pluto is 17.2 degrees. The orbital characteristics of planets evolve as the protoplanetary disk of gas and dust dissipates and as the young planets themselves migrate in the disk in response to their mutual gravitational influences and effects of material in the disk. Astronomers recognize, therefore, that the orbital appearance of a planetary system reflects its evolutionary story. The planetary system TRAPPIST-1 consists of 7 Earth-sized planets orbiting a small star, a mass of only 0.09 solar masses, about 40 light years from our Sun. First detected by the TRAPPIST telescopes, follow-up observations with IRAC camera on Spitzer and the K2 mission, among others, have by now determined the planetary masses to precisely between 5 to 12% and refined other properties of the system. Finally, support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below. Remarkably, the system is by far the flattest known. Its orbital inclination is only 0.072 degrees. The extreme flatness is potentially a very important constraint on the formation and evolution of the system. The system is also very compact, with the most distant of its 7 planets orbiting by only 0.06 astronomical units from its star. In our solar system, Mercury orbits more than 5 times farther away. In such a closely packed configuration of planets, mutual gravitational attractions will be particularly important influences on details like the orbital inclinations. CFA astronomers Matthew Heising, Dimitar Sasilov, Lars Harrisquist, and Anna Louisa Teo Humphrey used 3D computer simulations of the gaseous disk and planets to study a range of possible formation models, including several that had been suggested in previous studies. Knowing that the gaseous protostellar disk influences the migration properties of the planets, the scientists were also particularly interested in exploring what the minimum disk mass could have been for the TRAPPIST-1 system. They adapted the computer code Arepo, which has been used successfully in the past primarily for cosmological simulations. The astronomers concluded that, in agreement with their earlier speculation, the 7 planets probably formed sequentially, each one initially at a distance from the star where the temperature drops enough for water to freeze, and then migrates inward, accreting slowly on the way and stopping when its orbit is influenced by the presence of the other planets appropriately. Only a modest disk mass is required, about 0.04 solar masses, with the models also addressing the distribution of material within the disk, and moreover the astronomers can exclude disk masses more than about 15 times its value. The new work demonstrates how simulations of planetary systems can be used to infer remarkable details about how they formed and evolved. This was from Harvard-Smithsonian Center for Astrophysics by phys.org. Please leave your comments and thank you for your support.